Welcome to the Explainer. Today, we're totally demystifying one of the coolest topics you're going to tackle in your science class, spherical mirrors. We're specifically zeroing in on concave mirrors, how these curved surfaces literally bend light to shape what we see. I mean, we interact with them every single day, right? From car headlights to those giant satellite dishes on our roofs. But the physics behind them, it's kind of like a hidden superpower, and we are going to unlock the whole shebang right now.
Okay, let's dive right into this. We'll be hitting 5 key stops today: light and visibility, meet the concave mirror, rules of ray reflection, image formation explained, and finally, real-world uses. So let's kick things off with a quick thought experiment. Picture yourself standing in a completely pitch-black room. You can't see a thing. No hands, no walls, nothing. Then bam, a single light bulb clicks on. Suddenly, the whole room pops into view. But what's actually happening in that tiny fraction of a second? What's the exact physical mechanism connecting that light bulb, the objects in the room, and your eyes?
Well, the magic word here is reflection. Light travels in straight lines from a source, like the sun or a bulb, until it smacks into an object. That object then bounces or reflects the light right back. And when that reflected light hits our eyes, boom, that's what actually enables us to see things. It's basically a continuous cosmic game of pinball, and highly polished surfaces, like mirrors, are the ultimate bumpers.
Section 2. Meet the concave mirror, the shining spoon.
Now, you definitely don't need fancy lab equipment to study spherical mirrors for your science class. Honestly, a shiny metal spoon works perfectly to illustrate the two main types. See, a spherical mirror is really just a cutout of a reflective sphere. If that reflecting surface curves inward, like the bowl of the spoon where your soup goes, that's a concave mirror. Think of it like a little cave the light goes into. But on the flip side, if the surface bulges outward, like the back of the spoon, well, that's a convex mirror.
And this brilliantly illustrates the difference visually. Notice how the concave mirror cups inward, almost like it's trying to catch the light. This inward curve is absolutely crucial because it makes it a converging mirror. It takes all those incoming light rays and gathers them closely together.
To really grasp just how intense this converging power is, think back to that classic science class experiment. Now, quick disclaimer, never ever look directly at the sun or its reflection, right? But if you take a concave mirror, face it right at the sun, and hold a piece of paper just in front of it, something wild happens. As you slowly move that paper back and forth, you'll hit a point where the light forms this incredibly bright, sharp, tiny dot. Hold it there long enough, and the concentrated heat from that single spot of sunlight will literally make the paper smoke and catch on fire.
So, what exactly is that fiery little dot? In physics terms, that spot is the image of the sun, and we call its exact location the principal focus, usually just marked with a capital F. It's the precise point where all those light rays that were traveling parallel to the mirror's axis suddenly converge after they bounce off the surface. And the distance from the mirror itself, straight to that burning hot focal point, that's what we call the focal length.
Section 3. Rules of ray reflection. Mapping the bending light.
Okay, so if we want to predict exactly how an image is going to look in a concave mirror, like will it be giant, tiny, upside down, we just need to follow a few straightforward rules. First up, any light ray coming in parallel to the principal axis will always pass through the focus, or F, after it reflects. We literally just saw that with the burning paper. Rule number 2, a ray that passes right through the center of curvature, we call that C, gets reflected right back along its exact same path. And third, if a ray goes through the focus first, it's going to bounce off and shoot out perfectly parallel to the principal axis. These are basically your cheat codes for optical physics. You map where these rays cross, and boom, you found your image.
Section 4. Image formation explained. The core data matrix.
Now, what's really interesting about this matrix is the clear pattern that emerges when we apply those rules. Check this out. As you move an object from way out at infinity, closer and closer toward the mirror, the resulting image gets larger, and it actually gets pushed further away from the mirror. Plus, you'll notice that almost all of these setups create what we call real inverted images. That just means the image forms in front of the mirror, and it's hanging completely upside down.
But wait, there is one massive exception, a total rule breaker. When your object gets super close to the mirror, specifically squeezed right in between the principal focus and the pole, everything flips. The mirror completely stops making those real upside-down images. Instead, you get a virtual, erect, and enlarged image that looks like it's sitting behind the mirror. And this single quirky exception is literally a game changer for how we use these things in the real world.
Section 5. Real-world uses.
Physics in action.
It's one thing to sketch out ray diagrams in science class, right? But it is so much cooler to see this physics out in the wild. Let's talk satellite dishes. Remember how those parallel rays from the sun all converged at one point to toast that piece of paper? Well, satellite dishes do the exact same thing, just with data. They're essentially giant concave mirrors catching weak signals from space. Those signals hit the dish as parallel rays and reflect straight to the focal point, right where the receiver is sitting. By gathering all that scattered energy into one single powerful spot, it amplifies the signal so we can stream shows or get internet. How cool is that?
Now, let's completely reverse that thinking. What if we stuck a super bright light bulb exactly at the focus point of our concave mirror? Well, following our cheat codes, the light radiating out from that focus is going to hit the mirror and blast straight forward in perfectly parallel lines. And guess what? That is exactly how car headlights and flashlights work. You put the concave mirror right behind the bulb to catch the light, and it throws it all forward in one intense parallel beam to light up a dark road.
These mirrors are also absolute lifesavers in medicine. Dentists and opticians use them constantly. By taking advantage of that same converging trick, a dentist can use a tiny concave mirror to fiercely focus a beam of light onto one specific tooth. It gives them this incredibly bright, illuminated spotlight exactly where they need to look.
And finally, let's bring it all back to that special rule breaker we talked about. Remember? The one where if you put an object really close, between the focus and the pole, you get an upright, magnified virtual image? Well, that is the entire secret behind shaving and makeup mirrors. When you stand really close to one, your face is actually inside its focal length, so the mirror blows up your reflection while keeping it perfectly right side up, which, is definitely what you want when you're shaving.
So, we've totally unlocked how polished, curved surfaces can grab light and shape it to do everything from catching space data to lighting up our roads. But this leaves us with a really provocative question. We've mastered what happens when light bounces off a surface. But what on earth happens to that straight path of light when it goes through something transparent, like water or a glass lens? Does it stay straight or does it bend? Well, that phenomenon is called refraction. And let me tell you, it completely rewrites every rule of optics we just learned. But hey, that's an explainer for another day. Thanks so much for hanging out.